Objective 1, defining exponential and logarithmic functions. So in this video I'm going to discuss both the exponential parent function and the inverse of that, the logarithmic parent function. To begin though, if we consider the function f of x equals b raised to the x, or another way to say it, y equals b to the x, we still have a base and an exponent, only this time the exponent is a variable. If you notice, x is in the powers. We've only been working with x as a base raised to a power that's a number. Alright, so anytime you see a variable in the exponents, they're called exponential functions. So the parent function of an exponential function is f of x equals 2 raised to the power of x. So if we plot some points, or if we're given some inputs and we find some outputs, we can plot the graph of this and see kind of what it looks like, alright? So if I input -2, if I have 2 raised to the -2, that equals 0.25 or 1/4. So I'm going to put 1/4 in my output there. So the y value at x equals -2 is 1/4. Then if I raise it to the -1, it becomes 1/2. If I raise anything to 0, it equals 1. That's an exponent rule. And then if I raise 2 to the 1, it's just 2, stays the same. And then 2 squared is 4. If you notice, if I put 2 cubed, that's 8. 2 to the 4th, if I put 4 in for that x, it would be 2 to the 4th. That's 16. So if you notice, as the numbers, as my inputs grow by 1, the output grows substantially, right? It gets a lot bigger. That's what happens with exponential functions. So let me plot some of these, all right? So if I have -2 over here, I'm going to say that is 1/4, close to the x-axis. And at -1, it's a little bit higher than that. And then at 0, it's 1. You should notice a pattern now. It's going to start increasing at a greater rate. At 1, it's 2. 2, it's 4. 3, it's 8. And that's off the chart already. And then 4 and 16 somewhere up here. So if you notice, if I draw this line, this will extend to -infinity, and this will go all the way to +infinity, all the way up like that. Exponential functions will increase very rapidly because, again, the exponent is a variable, and that's where you're putting your inputs. All right, so this is an example of, this is f of x equals 2 raised to the x, the parent function. All right, so if we look then, and we go to the logarithmic function, the inverse of an exponential function, which is the logarithmic function. Here's some notes on logarithms. They were introduced by a guy named John Napier in the early 17th century. It's a way to condense or simplify calculations, especially when you are working with really big numbers like scientists or engineers do, that type of thing. And so they've created the logarithmic function to work with such numbers like if there's a huge earthquake, the way they measure that earthquake is a logarithmic function, a base 10 type system. So if you remember the exponential function y equals b to the x, or let's say y equals the parent function 2 to the x, then its inverse, y equals the log base b of x, or y equals the log base 2 of x. Alright, so if you notice a couple things, the base stays the same from the exponential function. It's still the base, log base 2 of x, and this is in the exponential, it's 2 raised to the x, and so it looks similar, but that is the inverse. Alright, so parts of a logarithmic function, you have log, the 2 in this case is the base, the 25 in this case is the exponent, or the power, and 2 is the output. Alright, that's the part of a logarithmic function. So in this case, in the parent function, 2 is the base, and then x would be the exponent. And then if it equaled something, then that would be the output. So let's graph the parent function of a logarithmic function. Alright, so the parent function for the logarithmics is log base 2 of x. Now, if I'm going to graph this, it's important to note, if I have because the log base 2 of x is the inverse of the exponential function 2 raised to the x, then I can take these inputs down here, and outputs and switch them for the logarithmic function. So I know these answers. -2 is the 1/4, -1 is 1/2, 0 is 1, 1 is 2, 2 is 4, 3 is 8, and 4 is 16. Now, I can switch them though. If you remember, this was an x and this is a y for the exponential function, so I can just switch these over. So my x's are now the outputs and my y's are now the inputs, all right? And so I'm going to plot my x value of 1/4 and go down to -2. And then I'm going to plot my x value of 1/2 and go down to -1. And then my x value of 1 is at 0. And my x value of 2 is at 1. My x value of 4 is at 2. And 8 is at 3. And we'll leave it there, all right? So this will go down to -infinity. And this will go all the way up and over to +infinity. All right, so if you notice then, inverses are symmetrical about the line y equals x, meaning that all the x values of one function become y values of the other function, and vice versa for the y values. And if you notice, here is an image of the parent function y equals 2 to the x, that's the exponential function, and then y equals log base 2 of x. All right? And so they're inverses of each other, and we've discovered that via graphically as well. That is the introduction to logarithmic functions and exponential functions. In the next video, I'm going to talk about how to switch forms, because that is necessary in order to solve these equations. Thank you for watching.